All right, folks, welcome to YFTT Talks by Engineers for Engineers. Today we'll talk about ultra-resilient and scalable vector search within YugabyteDB.
Yeah, and and I'm Kannan Muthukkaruppan, one of the co-founders at Yugabyte. It's my pleasure to say happy Friday to everyone. Welcome to another episode of the YugabyteDB Friday Tech Talks. I think we're kind of like at the 147th episode so of this series. Great to have you, Sandeep. My pleasure to introduce Sandeep, our VP of Engineering, and he heads the distributed storage and transactions layer for Yugabyte, and among other things. Vector search is also one of the projects that he's been closely involved with and leading. So it's great to have you on, Sandeep. Let's jump right in.
Thanks, Kannan. Hi, folks, again. So yeah, let's dive in. It's an exciting topic. Lots of action around AI and vector search within the industry. So happy to share what we are doing in this space and go into how we are solving some of these problems. Uh, So maybe to sort of kick things off, let's talk about what a vector database is. There's a lot of interest around this in the industry. So at a very high level, it allows storing unstructured data, but unstructured data, like, you could think about it as images, documents, music videos, and whatnot. They're best stored in object storage, but you want to be able to do similarity searches on them. So one way to store them is in a form of a numerical representation, which are referred to as vectors. You have a lot of AI models nowadays, and you can use those models to generate vectors or embeddings for some of these unstructured data. And then once you put that in a database like YugabyteDB, if you have vector indexes, you're able to do very efficient similarity searches on top of that, right? So for instance, like if you wanted to find images that have a bus stop, searching through a set of images is not something perhaps a database is good at, but once you transform those images into vectors or embeddings, and you have vector indexes on top of that, that makes it very efficient to query, make such queries. So wanted to quickly walk everyone through what RAG is. This is another term that gets tossed around quite a bit. And, what is RAG? Why do we need RAGs? And where do vector indexes fit in? So drawing your attention to the left side of the screen, right? So, LLMs are great and they have been trained on a bunch of data. OpenAI ChatGPT can answer a bunch of questions on the data that it's trained on. But once you ask a question that it is not trained on, then it can tend to hallucinate. So for instance, if you ask the LLM, hey, which club will Cristiano Ronaldo play in 23-24? And it's possible that the model was trained only till 2021, then it may have no idea, right? Uh, so how we augment this is, you have a vector database, uh, assuming you have additional context that you have put into this vector database, you will be able to pull that context in, feed that to the model, and based on that, it might be able to make an inference of, oh, there are these three documents that seem to talk about Cristiano Ronaldo and what is his next move going to be. And I can use that context to provide that information. So again, a high level flow would be you have a bunch of documents, you encode those documents using your favorite embedding model, uh, and then you put that in a database and create a vector index on top of this. And this makes it really efficient to query that data. And then your query comes in the form of, hey, which club is Cristiano Ronaldo going to play in? And use the same model to generate a set of embeddings, and that would be your input query. And you do a similarity search on the vector database. And the vector database itself is sort of looking at all the relevant documents and sort of generating a response. And so that's why RAG is relevant, because there is a certain amount of data that can be stored and queried, and LLMs are great at coming up with responses for data that they are trained on. But when you want to feed in additional context for that, that's when RAG comes in very handy. And so to illustrate this with an example, uh, take something like an application that has a question like, what is the percentage of fresh water in Antarctica, right? Uh, you often see that like the response could be something like this, like Antarctica's ice sheets contain like 90% of world's ice and 70% of fresh water. But how does this work in the context of PG, in the context of a vector database? So you have a bunch of documents which again talk about like Antarctica's ice sheets contain like 90% of. So you feed a document like this through an embedding model, and then you sort of store the generated embeddings, which are a collection of floats, a collection of vectors, into a database that has support for vector indexing. So something like Postgres with PG vector. And then when your query comes in, you have your query, which is what is the percentage of fresh water? You run it through the same model to generate an embedding for the query itself, which is another collection of floats or vectors. And you use this to perform a similarity search in the form of a query that looks a little bit like this. So you're selecting content where it's closer to a query vector from a list of documents that are persisted in the database. And you want to get like the top 5 results. So once you have like the top 5 documents that are closest, then you sort of feed that information back to the model, and it's able to use this additional context to answer a question like that.
And I think I just wanted to add a few comments, Sandeep. Firstly, the notion of sort of vectors and ability to do similarity searches and vector databases itself isn't too new. However, uh, I think the combination of things that is coming together, the advancements in the AI world of understanding these unstructured data and extracting features from it, the LLM models, the embedding models, that in combination with vector search is the one that's adding a lot of power. The second thing is, I mean, I think you can relate to vectors in sort of a two-dimensional space much more intuitively. For example, a query like find me my 5 nearest restaurants close to my coordinate. Now, whether the coordinate is represented as an x coordinate, y coordinate in a two-dimensional vector space, or a distance and an angle like an r and theta representation, that's where some of the embedding models may differ, how they represent a particular aspect of the input. uh, and that brings to attention two important things. That's the reason why the embedding model that you use to store your original documents better be the same as the embedding model that you're using to vectorize your query input. So if you had used XY representation versus R and theta, it's important that your query also matches that. And then the other dimension in picking these embedding model is like cost versus accuracy trade-off. Is the embedding model good at sort of processing English language documents only, or is it multimodal? Can it handle images and documents in the same vector space and so on? So a lot of interesting considerations. But yeah, please go ahead, Sandeep.
Mhm. Thanks, Kannan, for that context. So what is PG vector index, right? Which makes querying such data more efficient, right? For people familiar with Postgres or Yugabyte, it's just another index. You can think of your table having a collection of columns. And in addition to that, there is an extra column that represents the embedding, which is again a collection of floats. And you are essentially creating an index on the vector column itself. And there are like various distance functions that determine sort of what for different scenarios. And this is where like you could create, for instance, a vector index based on Euclidean distance or cosine distance. And that gives you a way to express the distance between two vectors. In addition to that, there are various indexing algorithms as well that make these vector queries efficient. One of the most popular ones is HNSW, which is sort of abbreviates to highly navigable small worlds, which has sort of become the state of the art in vector indexing, providing really high accuracy at very good latencies. Right. Uh, and given with this background, like what can you do with PG vector and Yugabyte itself, right? So YugabyteDB, is a distributed Postgres compatible database, uh, and what you can do here is not very different than what you would expect to do with non-vector data. So you can create tables. Here you can create tables with vector columns. And as you can see in this example, we created a table with image vector as one of the columns, which has 1,536 dimensions. So each each value here has 1,536 sort of floats. Once you create that, depending on uh, what type of distance is appropriate for your use case, you're creating an index using, in this case, the HNSW index type, and you're creating an index on the image vector column that you had created earlier. Once you do that, then you can load the data. Again, while loading the data, you can load it from files. You can load it using traditional SQL insert, select, and whatnot. Uh, PG Vector today does not support generating embeddings. So this is where you can use the extensibility of Postgres itself to use extensions or have an outside app that queries any of the model providers to generate embeddings for your data. And then you use that to load it into your database. And then you're able to do queries such as these, right? So where you're searching for images that are closest to your query image. For example, in this one, let's say you're searching for, something that's a cat, right? So your query might sort of convert that into a query like here, and then you're sort of doing this, n-dimensional, in this case, 1,536 dimensional search, and you're searching for nearest image, and then so you get images around this that sort of help you identify what it is. Uh,
So, Sandeep, there's a question coming in. It says, if you want to improve the accuracy of RAG, how can I tell whether the bottleneck is in the model itself or if I should be tuning the vector index parameters?
so with vector index, this being a SQL database in itself, like there is always the option of sort of doing an exact search, and that would give you uh, an the most accurate result, but at a slightly higher cost. And you also have the ability of tuning a lot of these parameters to sort of trade off between latency and accuracy of the results. For instance, PG vector and by extension Yugabyte do DB do expose options to tune the accuracy in a way where you get highly accurate results, but at a slightly higher latency. And this is where sort of HNSW index is interesting, where with HNSW indexing, the way it works is it's a multi-layer graph where at each layer, as you go down the graph, you have more and more nodes. So at the bottommost layer, you have all the vectors sort of represented. And it's a efficient way of traversing that graph to find out for a given input vector, what are the closest vectors. So the way you would improve the accuracy is by adding more connections, which is expressed using a few configuration parameters that we do expose as part of setting up the index and also as part of searching the index.
And so, so while While that covers maybe like one half of the question, I think the other half of the question was, can we tell if the bottleneck is in the model? And my intuition, and correct me if I'm wrong, Sandeep, is
Mhm,
right now the embedding itself, like converting the unstructured data to vectors,
mhm.
is itself not being handled at the PG vector layer. It's a
Yes.
complementary solution. You might pick Google's Vertex or Amazon's solutions or OpenAI models and so on. And so that would be more of a benchmarking type of evaluation of these models themselves, what the
Mhm.
cost and performance trade-off is in these models and accuracy. So I think that's a little bit beyond the scope of like where Yugabyte is trying to solve the problem space, and but it is an equally important consideration to compare the model benchmarks.
Yeah, you're absolutely right, Kannan. So that is one of the things that YugabyteDB is not doing today. Um, Obviously, there are services like OpenAI, Google Vertex AI, Bedrock that are doing a phenomenal job of it, and it really comes down to the model comparison at that level. Uh, with that, so how is YugabyteDB vector indexing different, and what does it provide on top of what PG Vector already has? Uh, so it is native vector search powered by PG Vector. So in terms of surface area, like everything that you would expect from Postgres, everything you would expect from PG Vector sort of exists with YugabyteDB as well. In database vector similarity search, you can query vector as well as relational data. You get the full Postgres compatibility, fully ACID compliant, so inserts, updates, deletes are immediately reflected. And it's open source, and we do have support for multiple distance functions and indexing methods. Uh, but where Yugabyte sort of builds on that foundation is uh, it the vector index that we built is sort of natively built for Yugabyte DB, and it's highly scalable, and it automatically is sharded across nodes, and that gives you the ability to horizontally scale and allows you to sort of run this at very high throughput, which we'll demonstrate a little bit later. Uh, and even in terms of the architecture, which I'll get into a little bit, we chose an extensible model because the space is evolving. Today, HNSW happens to be a popular indexing mechanism. But if there is evolution in this space, we wanted to be able to sort of quickly build on top of that as well.
Yeah, the
And
extensibility call out is super important. The way it's designed to be very pluggable. Sandeep, could you talk to like I think you mentioned that our starting implementation is with the HNSW
mhm.
as the kind of the underlying engine, while we share the interface in a compatible manner with Postgres, kind of the language level interface. But our implementation is HNSW. What is Postgres's default? Can you speak to that?
So Postgres supports two today. IVF flat is where Postgres or PG vector has started with, and then eventually support was added for HNSW because it's definitely the more performant index. And so we have directly started with HNSW with the architecture to extend beyond that.
Thank you.
And the last aspect is everything that Yugabyte DB was already doing in terms of resilience and global distribution. All of those properties sort of organically carry forward to the vector indexing solution as well. And so to get into how we actually do this, so uh, how we achieve Postgres compatibility, extensibility, and performance. Uh, let's start off with like we started with Postgres, so that's the that's our front end, right? So we are built on top of Postgres. So uh, Postgres and PG vector extension at the top, and this is what gives us sort of the Postgres compatibility. And then you walk in and then you create a table with a vector column. Now you have a tablet backing it. Again, this is the tablet where we have the DocDB LSM-based storage layer, and then also Raft replication for durability and consistency. Uh, so this is uh, Yugabyte DB as it existed even before vector indexing, right? Uh, And then now you sort of move on to creating a vector index. What we did is we built a vector index right alongside within the tablet, uh, so that you get the fastest or the most optimal performance, because a lot of times you are querying both vector data as well as some of the other metadata associated with those vectors, let's say the document ID and whatnot. And so having this co-location of vector index with the main storage was essential. And this gives you faster joins, you're able to push down filters and get the best performance. Uh, and under the hood, what we have is an LSM-based architecture, even for the vector index, and uh, the extensibility layer, where this abstraction on top of libraries such as usearch or HNSWlib, and in the future, maybe Fios and Scan being one of Google's vector indexing libraries, right? Uh, so this architecture was essential because this is what gives us extensibility and future proofs us. As this space evolves, we are able to quickly iterate and add support for more indexing libraries or algorithms. Uh, and so once the index itself is created, sort of the next step would be to load the data. Again, we're sort of going through the journey of that I described in the previous slide. So again, traditional copy data comes into uh, our vector index from Postgres. And here we write it to our in-memory buffer again. So here it's about like accumulating enough vectors in memory so that we can build a high quality index. But at the same time as writes come in, we do actually write it to our wall as well so that they are durable. Uh, and so this is what allows us to build high quality index where we accumulate a bunch of inserts in memory and then create vector index chunks. Again, if you're familiar with LSM-based storage, very similar in that aspect. And the last step of this journey is like you can select, and here the select again sort of comes in. And here, we are leveraging the amazing work done by usearch and HNSWlib to sort of query the vector index efficiently, load it if it's not already in memory, and then serve the results. And here we're able to sort of push down any filter predicates all the way down to the indexing library itself so that any filtering that needs to happen happens kind of deep down in storage. And that provides the fastest path. And as you can see, like over time, multiple vector index chunks could accumulate. So, we do have automatic compaction that basically merges chunks to provide a much more efficient performance, right? And we do all of this while sort of maintaining availability. So this is a tablet. YugabyteDB has RAF-based replication where the leader serves a lot of the write traffic, but then the raft log is replicated to the followers. And this is what sort of provides ultra resiliency. So if one of the peers goes down, another one takes over. Right? And how do we achieve scale and performance? Again, so this is sort of the same image that we saw before, the same architecture. But as data grows, the tablet automatically splits into multiple tablets, right? And this is something that automatically happens. You start out with one tablet, you have a small amount of data, but as you load data, if there is a need to split the tablet further, that happens automatically. And on top of that, like if you have a lot more data, or if you're looking for much higher throughput, then you can add nodes and you can have more of these. So in this example, you can see that we started off with one tablet, split into three, data grew even further, we split into 6 tablets, and now you can add nodes to scale that out further. And as you can see, like you have multiple Postgres nodes as well, sort of feeding into this, right? Uh, and then the queries can come in on any one of the Postgres instances or any one of the nodes. And you can see that you get the full advantage of the distributed uh, layer that we have, which gives you parallel execution, and that gives you maximum performance.
Sandeep, a few questions.
Mhm.
One was how much more efficient is querying on an index as opposed to doing a sequential scan? Is it something like log n?
It is it, it is it is log n, but it's actually it's algorithmically it's extremely fast because the number of nodes that we touch in our index scan are sort of much fewer compared to what we would touch on a sequential scan. But that's something that I will demonstrate.
Yeah, and that's exactly right. Like, you definitely want to avoid the problem of as your data set size is growing, you don't want an order n lookup performance. So yeah, that is the intent of the index. I had one more question,
Mhm.
Sandeep, on the previous slide. Like,
Yeah.
uh, obviously, like Yugabyte is able to now harness the power of multiple servers, their memory, and so on to not only parallelize some of the request side performance, but some of the vector implementations are very memory hungry, right? And
Mhm.
now you're getting to use the memory of multiple nodes, but even within a single node, does Yugabyte require the entire vector to be in memory, or does it follow the same paradigm of being able to use a block cache and keep kind of only the hot working set in memory and page in on demand and so on?
Yeah, so that is definitely one of the areas that we are innovating in. And the Yugabyte relational data or the non-vector data already has a block-based cache implementation. So we have a block cache where hot data is sort of maintained, and we are extending that to vector indexes as well, where not the entire vector index has to sit in memory, but definitely the as data is read, the hot data sort of makes its way into the block cache, and then automatically the cache is managed. Like core data does get evicted over time, right?
Thank you. I know we're a little bit at time, but I think it's I think we should do the demo. It's okay if we go shoot
Yeah,
over. Yeah.
yeah. So for the demo, I'll sort of maybe jump over the overview of the demo and just directly get into the demo itself, because we've got some great stuff to show. So maybe let's start off with like answering the scale problem. Uh, so what I've done is I've just taken our latest release 2.25.2, which is out there. And I said, okay, let's actually load this with the biggest data set that is there on VectorDB Bench. VectorDB Bench is a popular benchmark for vector searches. This is sponsored by, I believe, Milvus. So it said, let's take the biggest data set there, and I'm just doing a simple count star to show how many vectors this has, right? So that's 100 million vectors, right? And now we're actually going to query this, right? So let's start off by just, I want to show you what the query plan looks like. By the way, the tool that I'm using is called Beekeeper, another open source database query editor that is Postgres compatible. By extension, it's YugabyteDB compatible, right? So all I'm doing is, this is the magic set of vectors corresponding to an input query. So all I'm doing is running an explain plan on that. And what this shows is the query plan itself. What you will see here is that here, if you look at the query, I am selecting the top 100 vectors that are closest to a given vector. And this under the hood is doing an index scan, and it's ordering the results by this. So now we're actually going to query this. Uh, so I did an explain analysis to show various things here. One is you'll see the actual execution time. So that is 5 milliseconds. So it took us 5 milliseconds to query 100 million vectors and do a distance comparison against that. Another thing I would draw attention to is you'll see the index read request. So it needed one read against the storage layer, and the storage layer there, the graph was traversed to actually uh, show how to find the nearest vectors associated with that vector. And we'll just leave out the explain plan to see just the responsiveness of this, right? So that's what, sorry, I left out the 100 part. So that's how long it takes for querying 100 vectors. So to just demonstrate the difference between a sequential scan and index scan, so if you saw this, right, which is doing a simple count star, but it does have to scan the entire table. And you could see that there was a little bit of a lag. I could do an explain analyze here, and you will see that it takes on the order of a few seconds, right? But that's how long a sequential scan, which doesn't even include a distance computation, right? So that's on the order of like, 4 seconds or so, right? Whereas this is on the order of, like in this case, 15 milliseconds, but perhaps like on the order of 10 milliseconds or so, right? So that's the difference between having an index versus not having an index. But this is sort of a database, so just querying a random ID is not very interesting. So one thing I did is like, hey, there's a lot of action in the news about tariffs and stuff. So in this, I sort of made up a hypothetical scenario where, hey, there is a bunch of tariff documents that are chunked. And these documents themselves could also be in vector stored in YugabyteDB along with their embeddings. And here, let's assume that the user types in a question like, get me the tariffs for iPhone, right? That question would get transformed into a set of embeddings, let's say using OpenAI or Vertex AI. And with YugabyteDB, you're able to sort of search for all the semantically similar documents. And I also join it with some additional metadata about the document, along with some filters. So this is sort of the schema where for every document, we have some additional metadata. And if you look at the query, what I'm doing here is I'm looking at all the tariff documents, but then I want to filter on where the country code is US, and maybe I want to just check in the electronics. And I want to look at like something where, the current date is, between a couple of dates, right? So additional filters on top of this. So what you'll see here is like we are joining the vector query along with other tariff metadata to sort of get a sort of complete app like scenario working, right? So again, it's the same 100 million vectors. We queried that, and this basically was joined with other tariff metadata. And you can see the results. You can see the query plan where we've essentially done a join with, we have a nested loop join, and we have a filter on the PG vector. And we are doing an index scan on PG vector collection, which is where the embeddings data is. And then we have the tariff metadata here. And then we are essentially doing a join on that, on the document ID. Right. The last thing I wanted to show is it's not just scale, and it's also the unlimited throughput that you can unlock. So what I have here is I just took the exact same query and I put it into a simple script, and I'm running it against all the nodes, but I'm not I'm sort of gradually building up the number of nodes that the query runs again to give you a sense of what the throughput is and what the throughput can be as you scale the system. So here what we are doing is we added one node, and as you can see, the throughput was about 100 queries per second. And every 5 seconds, I'm adding more nodes, and you can see that we are sort of linearly scaling and adding and increasing the throughput further and further. And then after a little bit, I just add all the nodes, and you can see that the query throughput sort of keeps increasing. And so as you can see, so it keeps increasing to the point where, at one point we would basically running somewhere between 900 or so queries per second, right? So we started with somewhere around like 100, but as we added more nodes, we are getting a much higher throughput in terms of number of queries per second. Uh, I think uh, that's what I wanted to show. Hopefully, this gives you a flavor of what YugabyteDB's vector indexing architecture looks like and what it can do. Uh, but thanks for joining us.
Yeah, and it's worth calling out that all of this fits into the relational paradigm where you are not, in addition to the vectors, you're storing your other operational data, both your structured data as well as your document chunks, and the ability to join back and correlate and give you back the results in a single solution, as opposed to picking a specialized database just for the vector search capability and then a different database for your operational structured data store. This is kind of a unified solution with the power of SQL as your way to interact with the system. So it's really it really comes together nicely. But since there aren't any other questions and we're a little bit over time, I'd like to thank Sandeep for this excellent presentation, and thank everyone for joining us on another episode of this YugabyteDB Friday Tech Talk, and see you all on the next episode. Thank you very much, and over to Sandeep for closing remarks.
Thank you, folks. Thanks for joining us. You know, looking forward to what you will do with vector indexes on YugabyteDB.
Thank
Thank
you.